My great pleasure to present to you Peter Feller. He will be telling us about whatever the title is written there.
Thanks for the terse introduction. I much appreciate it. And thanks for having me, all of you. Yes, I want to talk about braids, quasimorphisms, and the slice-Bennequin inequality. And this is work in progress, actually, for a while. But there's one paper that is out that gets used a little bit in this. So I gave you this archive reference. This is joint work with Diana Hubbard. But that's actually from a while ago, 17. And what I will do is I will tell you what the writhe is, which you might know. And then I'll tell you a little bit about the fractional Dehn twist coefficient, which I've noticed low-dimensional topologists sometimes know less than the writhe, and this is a mistake because it's a very cool quantity. And then I will switch to a little bit more knots and concordance. And the last part 3, will be homogenization of concordance, homomorphism. And I actually decided to do the following. I give you a one-page executive summary of what you have to take away from this talk. That's really all there is to take away. And the point is the following. I will talk about the writhe. The writhe is, a group homomorphism from the Braid group, which I will define in more detail to Z. And you can geometrically calculate by drawing a braid, count the number of positive crossings minus the number of negative crossings. Here, 3 minus 1 is 2. And it has 2 properties that I want to mention. It's the unique group homomorphism, up to scaling, up to multiplying, to the reals from the Braid group. And secondly, it satisfies this interesting property, this interesting linear relation with the slice genus that I will define. So it relates to a not concordance quantity. And in a way, that's what I want to talk about, but for another quantity, namely the fractional Dehn twist coefficient. I will tell you along the way a little bit why I think the fractional Dehn twist coefficient is maybe even more interesting than the writhe. But the 2 theorems I want to talk about are, first of all, I will characterize the fractional Dehn twist coefficient as the unique quasimorphism of a certain type. The details will follow. And secondly, I will establish or tell you that the fractional Dehn twist coefficient also satisfies such a linear equation with the 4 genus of a knot. But details will follow. And please interrupt me if you have questions.
The inequality you wrote about the writhe and the 4 genus, that's true, like that's proved.
Sorry?
The inequality you mentioned right now, that is very surprising in my opinion. That's true.
Sorry, which one do you mean?
The writhe of a braid is less or equal than twice the 4 genus minus 1 plus the number.
Yes, that's the slice-Bennequin inequality.
No, it's just the bright minus n is exactly the self-linking number of the transverse knot represented by that braid. So it's...
sorry.
So
this is just a
thanks
for clearing that up. So I'm of the opinion that Rudolph's slice-Bennequin inequality is officially a braid statement. But if you're more on the contact side, you will.
Okay.
Every braid corresponds to a transverse link.
Sure.
There's one-to-one correspondence, and it's really just that. But I agree, it's actually surprising, and I think we're doing a disservice. We're so used to this for the self-linking number that we think, oh, it's just a slice-Bennequin inequality. I think it's a very surprising inequality, and I'm very glad I tricked you into once again see the wonder of it.
Okay,
so that's perfect for me.
That's great. But one more question. So if I have like a knot diagram, I can always define the writhe, right? It's like
yes, you can, but I'm really taking it for braids because you know, if you have a Reidemeister 1 move.
Okay, fine. Okay, I understand. Thanks.
You're welcome. Other questions? Okay, so then let me actually start with the talk. So the way the talk goes, the talk will always develop on the left-hand side, but, oh, I jumped 1, 2 ahead. On the left-hand side, but on the right, I have some additional information. So let me start by just recalling Artin's Braid group on n strands. And if you go about it algebraically, you might know that the first Braid group is the trivial group, the second one is Z cyclic, and then for n2 or greater, you have this beautiful algebraic presentation. But of course, as geometers, we think of braids as actual strands, so intervals embedded in a cylinder that hit every horizontal disk transversely and in the same points in the bottom as in the top, or put differently with these beautiful pictures. For B2, A1 corresponds to this generator. For B3, it's generated by two things that correspond to these two beautiful braids. I also gave you one for B4, and I remind you that group operation is given by stacking braids on top of each other. So A1, A2, A1 would be given by taking this A1 on top, stick A2, and then again A1. And I reminded you of the relations because I'm actually looking at braids up to isotopy. And I'm doing this fast because I dare assume that you guys have seen braids. But if I go too fast, please always feel free to interrupt me. I want to raise your attention to one particular element, the full twist. I've drawn some examples on 2 strands, on 3 strands. Here it is, and on n strands. And let me start by recalling just a little bit about what's going on with braids. So, for example, the center of the braid group is generated at least when n is at least 3. And the group gets interesting by this full twist. That's one little fact I will use. And secondly, let me also recall that the abelianization of the braid group is just Z. And explicitly, you can just map a generator to 1. And to set up notation, that's exactly what the writhe is. So you could algebraically check these relations. If you make everything commutative, just go away. But explicitly, this map written as writhe from Bn to Z that send the generator onto 1, standard generator onto 1. That's the writhe, algebraic way of saying what the writhe is. Further things I want to use, I can include the braid group on n-1 strands in the braid group on n strands, just by mapping standard generator to standard generator, or pictorially or diagrammatically take such a geometric braid and include it in a braid with one trivial strand to the right. And a picture which, if you're not too familiar with, I won't use much, but I'm talking about the fractional Dehn twist coefficient. So I'm talking about braids. Where do Dehn twists come from? It turns out that you can canonically identify the braid group with the mapping class group of an n-punctured disk. So that's a disk here with n punctures. And the mapping class group is the orientation preserving diffeomorphisms that fix the boundary pointwise, and you take its pi 0. And there's a particular element that you can think about. You take a boundary parallel curve, I call it alpha, and you do a positive Dehn twist along it. You twist along it. And this exactly corresponds to the full twist. And so my point will be, I will talk to you about the fractional Dehn twist coefficient. It's a quantity that wants to map the full twist to 1. So it's in a way a generalization of measuring how much you twist. Questions for my setup of braids? Otherwise, I switch to the fractional Dehn twist coefficient. So fractional Dehn twist coefficient, I'm actually only going to give you some properties. I'm not going to define it for you. So it's a map from the braid group to the reals, but it's an honest fraction. It lands in 1 over n times z. So rationals with the denominator at most n. And it is a homogeneous quasimorphism with defect at most 1. I'm going to, in a second, talk about what that means on the right. But let me first also note that the fractional Dehn twist coefficient satisfies 2 normalization properties. First of all, it maps the full twist once twisting to 1. And it also maps the Braid group of one less strands as embedded in the bigger group to 0. So we're essentially saying that the Braid group on less strands, it doesn't twist at all. Okay, so these are the normalization conditions. Now let's go back to this homogeneous quasimorphism business. And I just tell you generally what this means for a group. So if you have a group, if you have a map from a group to R, you call it a homogeneous map if it's a group homomorphism on cyclic subgroups of the group. So if you have a G to the K, you want this to be equal to K times F of G for any small group element G and any K in Z. That's homogeneous. What does quasimorphism mean? Well, you look at the quantity that is supposed to be 0 if you're a group homomorphism. So F of G times H minus F of G minus F of H. So that's this guy. And you ask for this quantity to be bounded over all group elements H and G. If it was 0, that's a group homomorphism. If it's bounded, we're talking about the quasimorphism. And I give this quantity a name. It's D of F. It's the defect of F. And the thing that I want to let you know is there are lots of those. So I kind of said that the group, there are only few group homomorphisms on the Braid group to the reals. It's all the writhe up to multiplicity. But actually on Braid groups, it's vast. So if you look at the space of all homogeneous quasimorphisms as mapped from the Braid group to R, that's a vector space, the homogeneous quasimorphisms are an infinite dimensional subspace. In fact, uncountably infinite. So there sits a little L1 in it. So I'm trying to tell you there are really lots of these. And the fractional interest coefficient is my favorite one. It's the one I want to talk about. Let me give you a little bit of a feel for the fractional interest coefficient by going into an example for the 3-stranded Braid group. So what does it mean? If I look at my quantity, and if I just look what it does on the generator, it actually comes out to be 0. And the reason is this normalization condition 2. So I have a Braid on less strands, and if you want, you can intuit this as this Braid does not twist. And I didn't tell you, but it turns out that homogeneous quasimorphisms are conjugation invariant. So for the same reason, if I take another generator of the 3-strand Braid group, I also get 0. But what about other elements? Well, if I take the product of A1 and A2, I don't get 0, I get a third. So you see this is no group homomorphism. And the reason is, I told you earlier, or by my normalization, if you take A1 times A2 to the 3rd power, you get 1 by normalization condition 1. And I'm homogeneous, so if I have a third of this, the number that comes out should be a third. Okay, a little bit of a feeling what this twisting invariant does. And maybe a little bit of background. This was, I guess, first studied by Gabay and Otal. I'm over here now to your right. Maluten is really the first who wrote it up for braids in a way that I use it, and there's some famous connection to contact geometry worked out by Hondo, Casares, and Matic. And let me just tell you that, intuitively speaking, this fractional interest coefficient really measures twisting along boundary and has some geometric properties. If you know what a right-wearing mapping class is, you might be interested in the fact that as soon as the fractional interest coefficient is positive, you are right-wearing, and vice versa, or almost vice versa. If you are right-wearing, the fractional interest coefficient is non-negative. I won't talk about this, but I will actually explain the property that the fractional interest coefficient being at least 1, then the braid cannot be destabilized. And I'm explaining this later. So this quantity has lots of geometric or topological information, and I would actually struggle to give you as much information about the writhe, but this has a lot of this information.
That's right.
And now,
just to check, by the fractional Dehn twist coefficient, you mean thinking of the braid as an element of the mapping class group of the disk?
yes.
Punctures. Yep. Okay.
But I mean, you don't, yes, for this translation, but in this talk, you don't actually need that. It's some map on the braid group.
Yeah, it's
but
just
yes.
So I know what you're talking about in my head.
Yeah. If right veering makes sense for a mapping class, and that's what I mean. But except for these two, I won't use any mapping class language. So you can take these formal. You can take the properties I've given you to the left. And here's my excuse why I only giving you these properties, which are somewhat well known. It actually turns out that they are characterizing, and that's my first result. So it turns out that there exists exactly one homogeneous quasimorphism. Let me call it F from the Braid group to R with the effect of F is less than 1. So that's this quantity that measures how much you fail to be a group homomorphism, such that 1 and 2 hold. So in other words, F is equal, F is equal to the fractional Dehn twist coefficient. So I won't explain this. I will just take it as a little bit of I justify with this that I never explained you a definition for the fractional Dehn twist coefficient. And the remark I want to make is that this kind of subtly depends on this defect, which you might not have an intuition for yet, but let me just tell you anyway that as soon as n is 3, if you pick any epsilon, there exist infinitely many, in fact, uncountably many of these quasimorphisms with the properties above. So linearly independent, homogeneous quasimorphisms from the n-braid group to R, with defect less or equal than 1 plus epsilon, and 1 and 2 hold. So whatever is going on in my characterization theorem, it somehow subtly depends on really pinning down the defect. Because as soon as you allow a little bit more, it's not at all unique anymore. There are many. The fractional Dehn twist coefficient is the simplest of the homogeneous quasimorphisms. It has the smallest effect. That's what I'm saying here. And I'm not explaining this. This follows from some geometric group theory. This follows from the same technology that gives you the fact that I had on the right. So that's my maybe very algebraic introduction to the fractional Dehn twist coefficient. It's this unique quantity that measures how much a braid twist. Questions for this setup? If not, let me start making the connection with knot theory. So brief reminder about the closure. Whenever you have a braid, you can associate a link with it. So a link is a oriented one manifold in S3, smooth, considered up to isotopy. And the point is, to every braid, I can associate its closure, written as beta hat. And to your right, I've summarized how this works. You take a braid, you draw it geometrically, and you build the closure, as I have done here. And here's a basic question excuse me about this. Here's a basic question you can ask. Here's a basic question you can ask about this connection. How do braid invariants relate to invariants of their closure? And I'm going to start with the writhe And I kind of already told you what's going on here. The writhe of a braid is related via this affine function to the for genus for all braids in Bn. And now I want this to be a knot with the closure a knot. If you don't like this assumption on the knot, and if you only know what the for genus is, you can always replace the for genus, which I'm defining in a second here. You can replace twice the for genus by 1 minus the four-dimensional Euler characteristic. And then everything makes sense for links, and I can forget about this with beta knot. But I think it's more, the important information is already there. If you restrict to braid, where the closure happens to have one component, so is a knot. Okay, let me briefly remind you what the for genus is. The for genus is defined as the smallest genus of surfaces, green F, where F is a surface smoothly embedded in the foreball, orientable, and the boundary of F is your knot. And I've drawn you a schematic picture over here. And if you don't work with this usually, let me just tell you it's smaller than the three-dimensional genus, where the three-dimensional genus is defined as the smallest surface in S3 that you can find with boundary the given knot. And to give you a very concrete example, down here, you see an F, a surface of genus 1 embedded in S3 with boundary, everybody's favorite knot, the trefoil. I want to very briefly mention that the slice-Bennequin inequality is very cool, and it's cool work of Rudolph, but it's a rather immediate consequence of what's known as the local Thom conjecture. And just for, which is a theorem by Kronheimer-Moravka. And just for sake of completeness, let me briefly make the statement. Statement is usually phrased as what the for genus of a torus knot is. Let me phrase it so that you see immediately the connection to the slice-Bennequin inequality, namely if n and m are co-prime, then the writhe of a braid beta and m is exactly equal to what I had before in the inequality, where the braid is this word. It's a1, a2 up to an minus 1 to the m. It's kind of like the full twist, but m is a different number than n here. And the point is, this is a braid which as a closure has a torus knot. And I did it in one example over here. For 2, 3, you get this braid. The closure is this beautiful thing. And you see its writhe is 3, and you can check that this equality is true if you know that the for genus of the trefoil happens to be 1. And if you don't know, you can use the inequality I have here to conclude this, because here's a surface of genus 1. And how do you prove that there's no surface of genus 0? Well, you shouldn't prove it that way. There are much easier ways, but you could use the slice-Bennequin inequality to conclude it. Okay, that's my brief summary of the closure. And this one cool relation I can give you for the writhe with smooth knot invariant. Questions about this setup? If not, I want to go to my new quantity that you didn't maybe appreciate as much yet, which is the fractional Dehn twist coefficient and relations to the closure of a braid. And yes, spoiler, as I already told you, the theorem will be, we have a similar slice-Bennequin inequality, but I first want to show you a little bit more of what's going on. And the first thing I want to talk about is if the fractional Dehn twist coefficient is strictly bigger than 1, then beta cannot be stabilized. And I should tell you what this means. So let's briefly go to the right and talk about stabilization. Stabilization is an operation that sends a braid to a braid on one more strands. It's not just the inclusion. I send an alpha to a last generator to the power plus minus 1 alpha. And let me do this in pictures. The point is, forget for a second the pink closure. You take a braid, you draw it again, one more strands, and you add one little crossing. Here it is. For the negative stabilization, you do the same thing, but you do a crossing with opposite sign. And the point is, this is interesting because if you do a stabilization, the closure that you get is an isotopic link. So if you look at this actual knot, you can isotope it back to the trefoil with one Reidemeister one move. And depending on your flavor of knot theory you like, you could say I could study knots via braids by Markov's theorem, which says if I have two braid closures, alpha hat and beta hat, they are isotopic if and only if they're related by a finite sequence of stabilizations and destabilizations, which is just the inverse operation, and conjugations of the braid. Okay, with that out of the way, you might see how you might be interested in destabilizations. And I'm telling you, oh, the fractional Dehn twist coefficient is able to tell you when you see a braid that you can't just trivially destabilize. And I'm actually, just to get a little bit of feel how the quasimorphism property comes in here, let me just give you a proof for this. So let's prove this. Is everybody on board with the statement? Because if I'm proving something, okay, what do I want to prove? I kind of go by contradiction. I assume my braid is a stabilization. So I have some n+1 braid where alpha is an n braid. Well, what can I do? I can tell you the following about the fractional Dehn twist coefficient. The fractional Dehn twist coefficient of beta minus the one of an minus the one of alpha is less or equal than 1. Why? This is exactly what I have from the equation for being a quasimorphism. Beta is an times alpha. So beta minus fractional Dehn twist coefficient of an minus fractional Dehn twist coefficient of alpha is less or equal than 1 because of this defect property. But now you're essentially done, because I told you earlier that on generators, it's always 0. That follows from property 2. And also, we understood this because by setup, we want the fractional Dehn twist coefficient also to be 0 on all braids on less strands. So this is also 0. So I get to conclude if I'm stabilized, then the value is less or equal than 1. Simple enough, I believe. Let me give you some more information. This is a result of mine and Hubbard's. We can say a little bit more. If the fractional Dehn twist coefficient is not only an absolute value bigger than 1, but actually bigger than n minus 1, then you realize the braid index. Then the braid index of beta is equal to n. Let me quickly tell you what's going on over here. The braid index, turns out every link is the closure of at least one braid, but there are many. So you can define a quantity, the smallest number of strands you need. By definition, it's the smallest n such that there exists a braid in the n-strand braid group such that its closure is your link. That's the definition of the braid index. And what this result tells you is, oh, if I'm looking at a given braid and it twists enough, then not only can it not be destabilized, but you can't ever write the closure as a braid as the closure of a braid on less strands. Three-dimensional properties. And if you know other definitions of the fractional Dehn twist coefficient, it's maybe not so surprising that three-dimensional topology could show up as related.
Peter, this result with Diana, was that in your 2017 paper?
That's in my 2017 paper. Yeah, maybe see 2017. That's correct. And it already featured a lot of concordance, but we're kind of focused on the three-dimensional stuff. And the observation is we can use what we did there also to understand a four-dimensional statement, which I'm explaining now. So for all, and you already know the statement, that the slice-Bennequin inequality also holds for this friend. So I take a braid such that the closure is a knot. I do it in brackets because I told you how to get rid of this assumption by using Euler characteristic rather than genus. Then it's true that the fractional interest coefficient is less or equal than twice the 4 genus of the closure of beta minus 1 plus n. Let me quickly into, well, I found this explicitly asked by a lot of authors over here, including actually Diana, and they were just wondering, does the fractional interest coefficient, similarly as the writhe, have a fine linear bound in terms of the 4 genus? And they kind of came from the following point. They observed the following. If you have positive braids, which we all love, these are the ones with only positive crossings, then the fractional interest coefficient is just bounded above by a linear factor in terms of the writhe. And then the writhe has a linear bound in terms of the 4 genus, so it's true. And same thing works a little bit less well in terms of the constant for quasi-positive braids. So for kind of a silly reason, it's just bounded above by the writhe. You start wondering whether this could hold for the fractional interest coefficient. But again, in general, for general braids, these quantities are completely independent. The writhe can be 0 and the other thing goes to infinity. So you certainly can prove it that way. But what I want to do in like 5 minutes is prove this to you with a little bit of cheating. Okay, questions about the statement of theorem B, maybe?
What is n0?
Sorry?
What is n0?
Wait, where are you looking at?
Less than or equal to
At the
something
statement
minus
of the
1
theorem.
plus n0.
Oh, no, sorry, that's just a period.
Oh.
It's exactly the same linear bound as for the slice-Bennequin inequality. But I'm very glad you asked, because this shows me that you're really checking on the details. So, okay, I told you about 2 quantities that satisfy a slice-Bennequin inequality that happen to be homogeneous quasimorphisms, one of which is a group homomorphism, so they are in particular. But I dare to ask, okay, I have 2. Which ones of these uncountably infinite quasimorphisms that the geometric group theorists can construct, which ones do satisfy either exactly the bound I was talking about with the 2 earlier, or maybe just in general, some affine linear bound? And you say, okay, that's a fair question. And maybe you wonder why I gave you theorem A and how it relates to theorem B. And here's the thing I want to tell you about. Namely, there's some relation. Let me give you the relation between satisfying such a bound and what the defect can be. I'm going to fix n, so I'm going to drop it from my notation. Let's just assume that you satisfy such a guy for all beta in Bn. And I'm not going to write closure of beta is a knot. It's implied. Then what I can prove, but I hope to improve, which is one of the reasons why this paper isn't out, I get a linear bound for the defect in terms of the constant. And that's kind of interesting to me, because I told you earlier, I understand that if you have small enough defect, then, and you satisfy these normalization conditions 1 and 2, then you can't be much. You actually have to be the fractional interest coefficient. By the way, you could say maybe you also want to ask this question without asking for this normalization condition, but that's a little bit silly. I mean, you know it's true for the writhe, then you can also do it for 15 times the writhe plus the fractional Dehn twist coefficient. So I think it makes sense to pick this normalization condition and then ask what you have. So remember by theorem A, I rewrote it for you over here. We know that if the defect is too small, then it's actually exactly equal to 1, and you have to be the fractional Dehn twist coefficient. That's what theorem A said. So the corollary here is that if F is a homogeneous quasimorphism, satisfying, well, the normalization 1 and 2, and furthermore, such that we have such a bound, for all beta in Bn, then F is actually already the fractional Dehn twist coefficient. This is just by plugging together the bound I have here. Sorry, I missed something. Such that this happens. Let me say it differently. Then C must be bigger or equal to 1 over n. Whoops. Minus 1. Why? If it were smaller, then the defect would be strictly smaller than 1, and then it doesn't even exist. No such quasimorphism exists. And if it's exactly C is 1 over n minus 1, well, then I would have to be the fractional Dehn twist coefficient, but there I know it's a 2. So you get some relation between, oh, if I have too much of an upper bound, I can't exist, and there's some restriction. This is not a perfect lemma, and it's not a perfect corollary. What I really want is the next conjecture, which is if you have any homogeneous quasimorphism satisfying your 2 normalization conditions, and you have that you satisfy the bound the fractional Dehn twist coefficient satisfies, I wish to have that only this fractional Dehn twist coefficient satisfies this. So that's my conjecture, which will give a nice characterization. So you can think of theorem A as the characterization using the defect of the fractional Dehn twist coefficient, and secondly, this conjecture, if true, would characterize the fractional Dehn twist coefficient using a slice-Bennequin type property. Okay, at this, yeah.
Just a quick question. Are there other quasimorphisms which have some sort of topological or geometric significance?
Very good question. Okay. If you come from the geometric group theory point of view and just abstractly construct them, it's not so clear. But what I'm going to do right now is I'm going to tell you a bunch of constructions of quasimorphisms that where you see a geometric coming from knot invariants in a way. So you could call that a geometric significance. It's related to a knot invariant.
Okay.
But other than the writhe and the fractional Dehn twist coefficient, just looking from the Braid theory side, I couldn't give you one that I know has geometric significance. Okay, let me tell you about another quasimorphism. Maybe for now I've been always, oh, there are only 2, and why would they ever satisfy a slice-Bennequin inequality? Let me tell you about the following guy, the homogenization of the signature. It's a map I'm going to do from B3 to R, and it's constructed using the signature at e to the I pi 3/4. So for this to make sense, I have to give you a very brief crash course on Levin-Tristram signature. That's over here. And it doesn't really matter what it is, but for completeness, it's the signature of a Hermitian matrix that is built out of a ciphered matrix for a link. If you know what these terms are, great. Otherwise, it's some knot invariant. And maybe you've heard of the classical signature. So this depends on the choice of a unique complex number. The classical signature is the one at -1. Great. And the one property I want to abuse by it is the signature, at least for almost all S, but I'm not going to be that precise here, does give a lower bound on the 4 genus like this. And here comes the trick. When you have a not invariant or link invariant, you can homogenize. What does homogenize mean? You want to define a quantity for a braid. Just take a braid. Here it is. And take the kth power. For example, over here, you see the example where you have a braid beta and you take the 3rd power. You take the closure, that's some link. You apply your link invariant. You divide by k and you take the limit. And for good not invariants, this limit turns out to exist, and that's the homogenization. And what's kind of nice about this is whenever you come from when you come from the signature, you get for free the slice-Bennequin bound. And so what I've done over here is, okay, I have such a quantity. If you want to normalize this to satisfy 1 and 2, I take some linear combination with the writhe. But if you set it up like this, then F satisfies 1 and 2. And it turns out that you have a slice-Bennequin type inequality that looks like this. And your F is definitely different from the fractional Dehn coefficients. I'm not giving you the details of this calculation, but I'm just telling you there are other Fs which do satisfy a slice-Bennequin inequality, for example, coming from the signature. It's just that the constant is much bigger, and I suspect if it drops down to 2, you are exactly the fractional Dehn coefficient. So with this, I want to come to my actual last slide. And tell you a little bit more about this homogenization construction. So let's go to the last slide. Whoops. Whenever you have a concordance homomorphism, let I be a concordance homomorphism. Now you say, what is a concordance homomorphism? I explained to you on the right. By this, I just mean any knot invariant, so a map from the isotopy classes of knots to R, such that 2 things are satisfied. I'm additive on connected sum. Remember, knots is a semigroup under connected sum. And I give you a lower bound for the 4 genus. And then, of course, we're all very excited about the signature being such an object. But maybe in more recent history, we're also very excited about the tau invariant. For purposes of normalization, I have to take twice tau, the S invariant, Rasmussen's S invariant, or more recently, the upsilon invariant by Oswald Stipschitz, Sabo. These are all concordance homomorphisms. And the little claim that holds true is if you first of all, the homogenization is always well defined. Oh, let me maybe define it. So homogenization of a invariant is simply defined as, again, you take the limit, k goes to infinity. In the end, I will divide by k. And what do? I apply the invariant to take the braid to the kth power, and then you take the closure. So I tried to do this over here. The problem is if it's only defined for knots, add a little extra, just the smallest possible braid you can find, like the smallest number of crossings, that makes your power of a braid into a braid that has as closure as a knot. So on the left, I took this little epsilon to just be A1, A2, A3. So then you close, you take the limit. This turns out to not depend on the choice of little epsilon. And the statement is, whenever you're in this setup, you have that you have a slice-Bennequin inequality. This kind of general theory of these things for all beta where the closure is a knot. And actually, you know, an example of this, the slice-Bennequin inequality. So here's an example. If you homogenize tau, or if you homogenize for some convention reasons minus S, you get back the writhe. So maybe you know that both tau and S can be used to prove the slice-Bennequin inequality. And this is what this is. So if you take this claim and apply it to tau or S, you get back the slice-Bennequin inequality because their homogenizations are equal to the writhe. And so now comes my own final and I guess only proper proof. Let me just prove for you theorem B, and it's going to be a silly proof. The silly proof is the following. It turns out that the fractional Dehn coefficient can be written as homogenization of some I, where I is a slice a concordance homomorphism divided by 2, plus the writhe divided by 2. And to give you a little bit more detail, that's also a result of mine and Diana. We observed that the fractional Dehn coefficient, which is originally defined combinatorially, and at the time we didn't know about the characterization I just gave you earlier, it's really 3-dimensionally or 2-dimensionally defined. It turns out that this is equal to the homogenization, this homogenization, where you have to plug t equal to 2 and minus 1. So, and if you notice, well, you can immediately write this inequality. This just follows from what's over there. 17, and now I'm done, because by the claim, this first term is 4 genus of closure of beta minus 1 plus n halves, and by the usual slice-Bennequin inequality, I get exactly the same thing again. So if I add these two up, I just get twice the 4 genus plus some constant. So my proof is done. So reinterpreting this quantity in terms of a homogenization of a concordance homomorphism is what allows me to make my conclusion. And that's all I wanted to say. I go to my last slide, which has 4 questions that I find interesting. And if you wonder how one ever goes about proving a claim such as the one I claimed earlier, on the left, you have a slide of how one does this. But let me stop here. And yeah, thanks for your attention.